Hi everyone, welcome to AI Crack channel. This is Akash Nungwa, your PGDBA 2026 mentor, and today we will be studying set theory lecture 1. So let's get started with our first lecture on set theory.
A set is a collection of well defined objects which are distinct from each other. So, two important things in this definition: well defined objects and are distinct from each other. So, what do we mean by well defined objects? That means all the elements of a particular set have one single common property. So, it's not like they are random, they're not random, they have one single common property attached with all the elements of a particular set, and they are distinct definitely. So, let's say we have 1 2 3 4 5. You cannot have a set like 1 1 1 2 3 and 4 and so on. You cannot have a set like this because these three elements are identical. So basically it should be like this: all elements should be different, or in other words you can say elements cannot repeat. One cannot repeat, two cannot repeat, three cannot repeat, and so on, right? So the very basic example is a set of students preparing for PGDBA. What is the well-defined object over here, well-defined property over here? That is, all of them are preparing for PGDBA, and they might have a different name. Let's say A, B, C, D, and so on. Okay? So every other person is different, but they have a common property that they are preparing for PGDBA, right? Now, having talked about definition of set, how do we represent them? So there are two forms. So the first one is kind of crude form, that is roster form. In this method, a set is represented by listing all its elements in curly braces and separating them by commas. So basically writing them in a very crude manner. Let's say we have a set of these elements: 1 2 3, 1 2 3 and 5. So we are writing them as 1 comma 2 comma 3 and 5, and covering them with curly braces. So this is the very crude form of writing a particular set. And again, here it's also mentioned, while writing the set in roster form, an element is not repeated. The order, however, doesn't matter. You can write this in the form of, let's say, 3 5 1 2. This set is same as this set, no difference, because order doesn't matter. But the thing is, there should be no repetition of elements, right? Now the other method, that is set builder form. But why do we need two forms for representation of sets? The first one is set builder form, the second one is roster form. Why do we need two forms? Why not just one? So the problem with the roster form is, let's say we have a particular set having 10,000 elements. In that case, it's humanly impossible, or let's say even if it's possible to write, it would take a long time to write all those elements in that crude manner, right? And it would be kind of inefficient. It would be very inefficient way to write a particular set. So that's why we need set builder form. And how set builder form works: so this is the set, this is the variable representing all the elements, and this is the common property attached with all the elements of that particular set, right? So let's take an example first and then we'll understand. The set of integers strictly between 2 and 8 is represented by. So the common property over here is all of them are integers and all of them are in between 2 and 8. So we have the common properties as they are integers, all the elements are actually integers, and they are between 2 and 8. So how to represent this in the set builder form? So this is our set. This is the variable representing all the elements, and x is less than 8 and greater than 2. We're not considering equality over here. We are assuming inequality over here. And the other property is x belongs to integers. So these are the two common properties associated with all the elements, and this is the variable representing all the elements. This is the set. So this is how we are going to represent our set builder form. Now, in this case, in this particular question, properties are explicitly mentioned. They are integers, they are between 2 and 8. But in this particular question, property is not given. But they have given the set in roster form to 5, 10, 17, 26. And we have to convert this into set builder form. But before converting that into set builder form, we need to understand what kind of properties are associated with these elements. There must be some common property among all these elements, right? So if I look at all these numbers closely, I can see that this is 1 plus 1. The first term is 1 plus 1. Second term is 1 plus 4. Third term is 1 plus 9. Fourth term is 1 plus 16. And fifth term is 1 plus 25. That seems to be 1 plus 1 square, 1 plus 2 square, 1 plus 3 square, 1 plus 4 square, and 1 plus 5 square. So if I want to represent this in terms of set builder form, so let's say this is our set. What should be the variable over here? Variable should be 1 plus x square. And the property is x is less than equals to 5 and greater than equals to 1. Right? This is our x value and x belongs to integers. So these are the two common properties among all the elements, and this is the entire variable representing the elements of the set. Or what we can do, we can write just y equals to 1 plus x square. So y is the variable representing all the elements of the set, right? Now let's move forward with the types of sets. The first set is null set, and as the name suggests, there's no element inside that particular set. So it is represented by this or this, basically having curly braces and nothing inside it, or with the term phi, with the symbol phi, not term, with the symbol phi, right? And there can be one special case. Let's say I am presenting a set with a null set inside it. In that case, this entire set is not a null set because it's having one element which itself is a null set. This set is a null set, but if we consider this as an element inside another set, in that case the outer set is not considered as a null set, right? So that one thing should be kept in mind. Now the second type of set is single set. A set consisting of single element is called a single set. So just like null set, we have just one element, let's say a over here, right? So that's a pretty simple definition over here. Now the third type of set is finite set. As the name suggests, a set having countable number of elements is a finite set. So let's take an example first. Let's take two examples. So the first is X is the set, and the properties are X belongs to 1 to 10,000 and X belongs to integers. The second set is Y, capital Y, and Y belongs to just natural numbers. Now in this case, we can clearly see that there are 10,000 elements from 1 to 10,000 and all of them are integers. Right? So we have 10,000 elements over here, but over here we have no count because natural numbers are infinite actually. So we have no count of elements in this particular set. So this set is infinite set, this set is finite set. So anything which can be which is countable, maybe it can be a lakh, it can be 1 cr, it can be anything, but if it is countable, it is limiting somewhere, it is stopping somewhere, in that case we can say that it's a finite set. But in case of natural numbers or integers or whole numbers or real numbers, they're not stopping anywhere, right? In that case we cannot say that it's a finite set, it's actually an infinite set. So this is what we were talking about. A set having infinite number of elements is an infinite set, obviously, right? Now the next type of sets are equal sets. So two sets A and B are considered equal if every element of A is there in B and vice versa, right? So we have two sets A and B. Let's say we have 1, 2, 3, 4. For both of them to be equal, every single element of A should be present in B and vice versa. So basically that means the length of or the number of elements in A is same as number of elements of B, and also all the elements of A are also present in B. 1, 2, 3, and 4. So we have 4 elements over here, 4 elements over here, and all the elements of A are also present in B. In that case, we can say both A and B are equal. Now the other kind is equivalent sets. In case of equivalent, we have just number of elements equal in both the sets. Let's say we have A and B. So the first set is 1, 2, 3, and 4. And the second set is A, B, C, and D. So the number of elements in B and number of elements in A both are equal. So they are called as equivalent sets. Now the interesting thing is all equal sets are equivalent sets because that is the inherent condition that number of elements in A and B should be equal. So all equal sets are equivalent sets, but not vice versa. All equivalent sets are not equal sets. Okay. Now let's talk about subset and superset. So the definition says, let's say we have set A and set B. If all the elements of A are also present in B, if all the elements of A are also present in B, In that case, A is a subset of B. Right? Regardless if both A and B are equal. Let's say A and B are actually equal. A is 1, 2, 3, and 4. And B is also 1, 2, 3, and 4. So all the elements of A are also present in B. In that case, regardless of both of them being equal, you can say that A is a subset of B. That is the basic technical condition. Okay. Now, on the other hand, we can also say that B is a superset of A, but usually we represent A as a subset of B and not the otherwise. Otherwise, both of them means the same, but we usually use term A is a subset of B and not B is a superset of A. Okay. Now, sometimes we use this for subset and sometimes we use this as subset. So, what is the difference between them? So, in this case, number of elements in A are lesser than number of elements in B. That is the basic condition. And in this case, number of elements in A may be equals to number of elements in B. So, basically, in this case, we are including the condition that A and B can also be equal. But in this case, we are strictly taking all the cases where number of elements in A are lesser than number of elements in B. So basically they both won't be equal in any case in this particular case. In this particular case, they may be equal because we have used this equality sign, but in this case, we haven't used that equality sign over there. So they won't be equal. So number of elements in A would always be less than number of elements in B, considering that A is a subset of B, right? So that is the basic definition of proper subset. In case of proper subset, A is a subset of B, but A is not equal to B, then A is a proper subset of B. That's what we discussed. So in other words, we can say number of elements in A is less than number of elements in B, or we can say that A is a subset of B, but A is not equals to B in any case. So both these conditions are true, or you can represent that NA is less than NB and A is a subset of B. Both means the same. Okay. So both of these conditions or both of these conditions means the same and gives us proper subsets. Now the other case is improper subset, and that includes this particular case as well, where A equals to B. A can be equals to B. So that is just one additional case other than all the cases including in the proper subset. Right? Now let's solve this particular question. Let A equals to 1 comma 2 comma this element comma 5. Which of the following statements are correct? Now let's first try to simplify our set A. This is 1 comma 2, this is B and comma 5. B is actually 3 comma 4. So what we have done is we have represented 3 comma 4 as B, okay, to make things simpler. And before proceeding with the options, let's try to understand what these symbols means. The first one is easier. We have just studied that this is actually a subset. So what do we mean by subset? We mean when we're writing 3 comma 4 is a subset of A. That means individually 3 and 4 are a part of A. They are present in A. When we see 3 comma 4 as a set is a subset of A, in that case we mean individually 3 and 4 are inside A, right? So this is what we mean when we are using this particular symbol, right? So in that case, do we have 3 comma 4 individually inside A? No. This is our A. Can we see 3 comma 4 over here? No. So that's why A is not correct. Now if we talk about option B, when we are saying belongs to A, this means we are saying B belongs to A. B is inside A. That basically means in crude language, in raw language, it means B is inside A. Is B inside A? Yes, we have 1 comma 2 comma B comma 5. So B is inside A. So that's why B option is correct. If we talk about the C option, so we have this as a subset of A. Now, when we say this as a subset of A, that means individually B is inside A. Is B inside A? Yes, we just saw that B is inside A. So that's why C option is correct. Now, the fourth option is D option. We have 1 comma 2 comma 3. It belongs to sorry, is a subset of A. 1 comma 2 comma 3 is a subset of A. And when we say is a subset of A, that means individually 1, 2, 3, all of them are a part of A. But is it correct? 1 is part of A, yes. 2 is part of A, yes. But is 3 a part of A? No, it's not. It's actually a part of B, which is inside A. So technically 3 is not a part of A. So that's why D is not the correct answer. So we have B and C as the correct answer. Now let's talk about number of subsets. The total number of subsets of a finite set containing n elements is 2 raised power n. And let's try to understand how do we get to this particular number. So let's say we have one particular set A equals to 1 comma 2 comma 3 comma 4. So let's make some blanks over here. All are probable subsets. Now what I'm doing, I'm filling all these blanks with these numbers. And I may or may not fill with these numbers. Let's say I fill 1 over here, but I'm not filling 2 over here. I'm filling 3 over here and not filling 4 over here. Over here I'm filling 1 and 2 and 3 and nothing over here. And over here I'm filling nothing. I'm not filling anything. I'm filling 3 and filling nothing. So this particular set became 1 comma 3. This became 1 comma 2 comma 3. This became just 3. All of these elements, all of these subset, all of these sets, sorry, all of these sets, this set and this set, all are subset of this particular set, right? Agreed. All these sets are actually subset of this one. And how did we create it? We chose either to include every element or not. We chose to include one over here. We chose not to include two over here, right? So it gave us two choices, either to include or not. So if we have four blanks over here, we have choices to include or not. We have choices to include or not, right? We have choices to include or not. We have choices to include or not, right? So this is how our choices are being made. So for every blank we have two choices. So if every blank has two choices, so by the basics of counting, we have actually 2 dot 2 dot 2 dot 2, that is 2 raised power 4. And how many number of elements are there in this particular set? We have 4. So 2 raised power 4, that means 2 raised power n for n number of for a set having n elements. For a set having n elements, the total number of subsets are 2 raised power n. How? With the help of basics of counting and giving choices for each blank, right? That part is clear. Now the second part is the total number of proper subsets of a finite set containing n elements is 2 raised power n minus 1. Why there's a minus 1 over there? So again, let's take this example only, 1, 2, 3, 4. Now there must be a case where nothing is over here, nothing is over here, nothing is over here, nothing is over here. So basically I'm choosing not to include any element in this particular subset. So this would become actually a null set, right? Now there can be other case as well where in all the elements I'm choosing 1 comma 2 comma 3 comma 4. I'm choosing all the elements over there. In that case this becomes an equal set, and when it becomes an equal set, then it becomes an improper set. So when we are saying proper subsets, in that case this one particular subset which is equal set, nothing but equal set, should be excluded, right? So in that case there is this minus 1. So 2 raised power n is the total number of subsets for a particular set having length n or having number of elements n, and minus 1 basically subtracting this one particular set, where which is nothing but an equal set. Okay.
So today's lecture was till here only. Next lecture will be the last lecture of set theory, and it will be a bit longer as compared to the first one. So let's meet in the next lecture. Thanks for watching.